the directional derivatives. Directional derivatives. So the necessity for gradient and directional derivative stems from the fact in the first example we were purely moving in the x direction, and when we purely move in the x direction we treat y as a constant, and when we purely move in the y direction then we treat x as a constant, then we find derivatives. But what if we just don't purely move in the direction of y nor x, but we move in some specific direction? For example, we move in this direction. Then how do we calculate the slope? For example, let's say this is we are moving in this direction, and we want to find the slope at any of these points. Then how will we do it? And in order to do that, I first want to modify this function, these derivatives, and I want to show them in terms of vectors. First, instead of xy, we will show them as a components of a vector. This is a and this is x, y, right? xy. And then we will try to build these formulas by treating x and y as the component of the vector, as the components of the vector. For example, let's take this one. I will write it, then I will explain. This is our vector. Then we have h. Then we have unit vector. And yes, that's it. And then we have f, a. Then h, limit goes to and let's see how actually it translates into the same thing. So we had a which was xy, and this part simply means xy plus h, and we can build our direction, this vector, in a way that we can make sure we are only moving in the x direction or we're only moving in the y direction. For example, if we are only moving in the x direction, then it will be 1, 0. The x component will be the one that we will add some h, and then we will see how this very small h change in the x affects the function. Then it will be x plus h and y plus 0, right? Then it will be the same thing. Y didn't change, but x changed h amount. And with the same analogy, if we do it with respect to y, then we'll have a vector a, again the same thing, minus f h, limit goes to 0, limit h goes to 0. In this case, the direction that we are moving will be purely in the y direction. We won't move any step in the x direction. In this case, we purely moved in the x direction. That's why there was no change in the y component of the vector. And in this case, it's the same, but in this example, we are only moving in the y direction, because if, for example, if we again take a look at this example, then we will see vector A plus, which is xy, plus h. In this case, our vector will be 0, 1. Then it will be x plus 0, y plus h. Right? So what we did here, we represented the move purely in the x direction as a vector, because this is also vector, right? If we go parallel to x, this is also a vector, and we represented this as a vector. And if we go also in the y direction, this is also a vector. It's a vector parallel to y. Then in that case, the direction that we are moving will be this vector. So in this case, this vector is parallel to the y, and we are moving purely in the y direction. And here, the vector is purely in the parallel to x, and we are only moving in the x direction. So it simply means we are moving in a direction of a vector that is parallel to x. And if we want to, for example, if you want to take any direction, then we will just write f. Then it's computed as f derivative of f(v), f x0 y0 in the direction of v. In the direction of v, the derivative of f of x0 y0 in the direction of v is equal to, and this is a vector, and we can write it as dfv, because we don't need to write this. We already represent this with the vector. Oh, no, that was a mistake. This vector is different than this vector. So then the derivative of a point in direction of a vector is equal to, and this is simply vector A. This is simply f yeah, this is the formula. And this is equals to gradient of f at this point multiplied by that vector. This simply equals to this. And in the next video, we will actually prove that this is the same as this. In the next video, we will prove that.